In today's lesson, we are going to be looking at binomial distributions. So binomial distributions are another specific type of probability distribution similar to the uniform distributions that we looked at in the previous example or previous lesson. This is going to be a little bit different though, so it's not going to be quite as easy as uniform distributions, but it is going to involve concepts that we've already looked at. So just as a warm-up, there is a 70% chance that an allergy drug will be effective on a person suffering from the allergy symptoms that the drug treats. What is the probability that out of 10 random people, it is effective on 7 people? So I'm not going to go into too much detail on this one, but this is just kind of a warm-up question that we will revisit once we kind of learn a little bit more about binomial distribution. So take a second, think about it. If you want to pause the video, to think about how to calculate this, you can. We will come back and look at this scenario or the distribution for this scenario, which will allow us to calculate this specific outcome. But moving on, what that warm-up involved was what was called Bernoulli trials. So these are trials involving the probability of a compound event that is made up of the same event multiple times, where the probability of the individual trials always stays the same. Right? So that's looking at independent trials. So we're basically dealing with some independent events because the probability does not change. And there are only two possible outcomes in Bernoulli trials. Either it is a success or it is a failure. So if we think about the last one, it was independent because it was a 70% chance, and that didn't change depending on who the person was. It was a 70% chance of it working. That also helps with the two possible outcomes. There's a 70% chance of it working. There's a 30% chance of it not working. And it's the same event multiple times. Person 1, does it work or does it not work? Person 2, does it work or does it not work? Person 3, does it work or does it not work? Right? So a similar idea, it's the same event multiple times. They're independent events because the probability is not changing per person. And there's only two possible outcomes, success or failure. And that is basically the characteristics of binomial distribution. And the characteristics specifically are it has a specific number of independent trials. So again, remember, independent trials means the probability does not change. It is not affected by what happened previously. And now it is also mentioning there are only two possible outcomes, a success or a failure. Right? We refer to that as P and Q, success or failure, and P plus Q has to equal 1. Right? Those are the only two possible outcomes. All the possible outcomes have to add up to 1. So the probability of 0 or probability of success happening plus the probability of failure has to add up to 1. Now to calculate the probability in a binomial distribution might look a little complex. Right? The probability of each outcome, we have it broken down into a combination, which is the total number, which is n choose x. So n looks at the total number of trials. X is referring to our specific outcome. Px is the probability of success. And Q is the probability of failure. And the probability of success and failure is they're both raised to powers or raised to exponents, x being the number of successful outcomes and n minus x being the number of events that are considered failures. So let's go back and look at that warm-up, looking at the 70% success rate, which meant a 30% failure rate. Right? The drug did not work 30% of the time, or there was a 30% chance that it didn't work. So using our specific formula now that we've talked about for binomial distribution, which was the n choose x times px times q n minus x, let's look at that in terms of each specific outcome. Remember, the probability distribution talks about the probability for every possible outcome. So if I have 10 people or 10 people being selected, I could have the drug working on anywhere from 0 to 10 people. So for 0 people, I have 10 choose 0 multiplied by the probability of success, or 0.7, raised to the power of 0, because no, it's not successful on anyone, times 0.3, which is the probability of failure, raised to the power of 10, because there are 10 people and it fails on all of them. And in this case then, it works out to 0.00059%. For one person, it would be 10 choose 1 multiplied by the probability of success. So 70% chance working on one person, and then a 30% chance for 9 people. So we get 0.014%. For 2 people, or the probability that it works on 2 out of 10 people, we have 10 choose 2 multiplied by 0.7 to the power of 2 times 0.3 to the power of 9, or not 9, 8. So 2 people, it's a success on, 8 people, it's a failure on, 0.145%. And again, it is the same calculation over and over again in this probability distribution. So it is a little bit tedious and it is a little bit repetitive. I'm going to keep on showing each individual one or some of them. I'm not going to go through and do all 10, but just enough to hopefully allow you to see the different steps on how to actually go through and solve. So again, 10 choose 4 times 0.7 to the power of 4 times 0.3 to the power of 6 is equal to 3.67%. Again, I'm going to skip over and go right to 10. 10 choose 10 times 0.7 to the power of 10 times 0.3 to the power of 0, or 2.8. So basically that's saying there's a 2.8% chance that it works on all 10 people. Now, if we go back up to this warm-up and we take a look at how this actually works. Well, I have 7 people. And if it's a 70% chance that it works, then it's 7 or 0.7 times 0.7 times 0.7 times 0.7 times 0.7, 7 times. 1, 2, 3, 4, 5, 6, 7. But then we also have to consider that it fails on 3 people. So 30% chance times 30% chance. So that would be one scenario. However, it doesn't say which people it works on, right? We're assuming that it's working on the first 7 people and failing on the last 3. So what we have to do to consider the different possible combinations of people, we're going to multiply now by 10 people choosing 7 of them for it to be successful on. Again, it doesn't matter the order because we can't tell the difference between successes, so arranging it doesn't matter, but selecting a group of 7 people from 10 to basically allow it to be effective, we do have to account for. So again, these are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 people. We're choosing 7 of them for it to be successful on. So that's why we're multiplying by the combination at the end. So that is basically a kind of a long form of what we're doing in that table. Hopefully it allows you to see how that kind of relates to this scenario, because when looking at it at the table, it might not really make sense. With binomial distributions, we can calculate the expected value. Right now, we are still allowed to do the sum of. So we are still allowed to do that the expected value is equal to the sum of each outcome multiplied by the probability. But if you go back and you look at that table, well, that requires us to actually fill out the entire table and then take the 0.00059% times 0, 0.01% times 1, and so on, and add them all up. With binomial distributions, there is a quicker way to do this so that we don't have to do this. Right? This would, while it would work, just tends to be long and complicated, especially with looking at how we had to calculate the probability. So here, the expected value, again, EX, is equal to N, which is the number of trials, times P, which is the probability of success. Which does make sense. We take the probability of success, multiply it by the number of trials. That's how many we're expecting to get, or that's how many successes we're expecting to get. So let's take a look at the probability, or this example. The probability of making a basketball shot for a player is 0.80 or 80%. If the player attempts 5 shots, A, find the probability distribution for the number of shots that they make, graph it, determine the probability of them making more than 2 baskets, and then calculate and interpret the expected value. So the first thing we want to do is create a probability distribution. So looking at the number of shots made, that's our random variable. If we're attempting 5 shots, then I can make anywhere from 0 to 5 shots. A couple things we want to consider. Looking at that, we'll actually go back up. If we go back up to the scenario, we have 5 shots, which is our N value. And we have the probability of making a shot, which is 80% or 0.80. So that means that P is 0.8 and Q would have to be 0.2. 80% chance we make it, 20% chance we do not. So this is a binomial distribution. Each shot is independent of the previous one, and we're making the assumption that it's only a success or fail. It either goes in or it doesn't. So let's go through and calculate or create the probability distribution for the number of shots. So using our formula, 5 shots, choosing 0 of them, multiplied by an 80% chance of success to the power of 0 because I didn't make any, multiplied by 20% chance of not making it to the power of 5 because every shot missed, 0.032%. And then again, I know it might seem tedious of me writing each one out, but hopefully it helps kind of show that repetition and allows you to see where we're getting these values from each individual time. So 5 shots, choosing 1 because 1 shot is successful, 80% to the power of 1 successful, 20% or 0.2 to the power of 4 unsuccessful shots. So this ends up being 0.64%. Now keep in mind, if you go through and actually calculate it, you probably get a decimal. I've then multiplied it by 100 to get these percents. 5 choose 2 times 80% to the power of 2 times 20% to the power of 3 gives me 5.12%. 5 choose 3 times 0.8 to the power of 3 times 0.2 to the power of 2, which is 20.48%. And hopefully you're starting to see a pattern. Right? There's kind of a pattern as we go through this. The exponents are increasing on one and decreasing on the other. And when we're choosing, we're increasing from 0 going all the way up to the total number, or n. So 5 choose 4 times 0.8 to the power of 4 times 0.2 to the power of 1, 40.96%. And 5 choose 5 times 0.8 to the power of 5 times 0.2 to the power of 0 gives me 32.768%. So this is the probability distribution for shooting 5 shots in this given scenario. I can see the probability of each possible outcome, which is making anywhere from 0 to 5 shots. Now, if I want to go through and graph this probability, again, I could 0, 1, 2, 3, 4, 4, 5. So number of shots made. We have our probability on the y-axis. We say 10, 20, 30, 40. So for a 0 shots made was less than 1, so we'll just draw a line along the bottom. 1 shot made is 6.4, so a little bit higher, so we have a 1% chance. 2% or 2 shots is about 5%. 3 shots is about 20%. 4 shots is about 41%. And 5 shots is about 32%. So we can see how this kind of probability distribution looks. We see that we're definitely geared more towards making almost all of the shots or the majority of the shots compared to missing, which makes sense given the probability. We had a high probability or a high chance of making the shots, 80% chance of it going in. So that's what our probability distribution looks like graphically. Now we can also use the table to help us. So here we have the table. I went through and did this in Google Sheets. There will be a video posted that will allow you to kind of use Google Sheets to make all these calculations if you really need to. Now, what is the probability of the player scoring more than 2 baskets? So more than 2 means 2 or greater than 2, so that means 3, 4, or 5 baskets. Specifically in our table, it's looking only at these values. So the nice thing about this, when we have our probability distribution table, anytime we're asked one of these questions, now we just have to go through and add up the specific values. So more than 2, so that's going to be 0.2048 plus 0.4096 plus 0.32768. When we add all of those up, we have a 94.2% chance of scoring more than 2 baskets. Now, similar to other scenarios, we could do the indirect if we really wanted to. So the probability of scoring more than 2 baskets is going to equal 1 minus the probability of scoring less than or equal to 2 baskets. Right, so I'll highlight those in a different color. So those are all the other outcomes. So 1 minus 0.0512 minus 0.0064 minus 0.00032. Either way you look through it, in the end, 94.2%. Now, in this case, whether you do one or the other, it might not really matter because you're not really calculating the probabilities anymore. You're just basically looking at your table, your distribution, and then adding up the specific values. Calculate and interpret the expected value. So again, like we mentioned, we could go through and do each outcome multiplied by the probability. So 0 times 0.00032, you get 0. 1 times 0.0064, and we get 0.0064. And go through the next one and the next one and add them all up. Now, for sake of time, and because I don't want to go through and do any of the other multiplications, we do have that new formula for the expected value, which is n times p. The number of trials, so in this case, the number of trials is 5 multiplied by the probability, which makes sense. If we're making 80% of our shots, we have 5 shots, we would expect to make 80% of those shots. 5 times 80%, which is 4. So therefore, we expect to make 4 baskets out of 5. And if you were to go through and do this XPX and add them all up, you would find that you get the same value. Just it's a lot easier now to use this formula rather than having to go through and do all those different calculations. Last example, so in a manufacturing process, it is estimated that 0.1% of products are defective. A client places an order for 25 of the products. What is the probability that at least 3 of them are defective? And how many in the order are expected to be defective? Well, probability that they're defective, or at least 3 of them are defective. So because we're looking at this, we can see that it is either a success or failure. It's either defective or it's not. In this case, so then the probability of it being defective, or P, is 0.001. And the probability of it not being defective is 0.999. Now, one thing you want to be careful of, just because it's the probability of success does not mean it's the opposite, right? Success is what we're looking for. So if we're looking for them to be defective, then the probability or the probability of success would be a defective item. The probability of failure in this case would be a non-defective item. So again, success is what you're looking for. So we're looking for defective. So that's our success. So we could go through and do the probability of each outcome, right, of x, that is x is greater than or equal to 3, right, for at least 3. Again, that's going to be too long. So it's easier to do the indirect method, which is going to be 1 or 100% minus the probability of 0 minus the probability of 1 minus the probability of 2. So in this case, we have 1 minus, we have 25 choose 0 times 0.001 raised to the power of 0 times 0.999 raised to the power of 25. 25 items that are not defective. Minus probability of 1, so 25 choose 1 times 0.001 to the power of 1, 0.999 to the power of 24. Minus 25 choose 2 times 0.001 to the power of 2 times 0.999 to the power of 23. Again, when we go through and we calculate, subtract all of these, we should find that it is 0.12345 So a very low probability that at least 3 of them are defective, which makes sense given that the probability of a product being defective is very, very low. Now B, how many in the order are expected to be defective? So I could go through to the whole probability distribution table for all 25 items and add them, multiply them by the outcome, add them all up, or I can use my quick way, NP. So I have 25 trials or 25 items times the probability of them being defective. This gives me 0.025. So therefore, we'd expect 0.025 of a part to be defective. All right, so a very low number of outcome or number of items that we'd expect to be defective. Again, we can use Google Sheets to basically do these probability distributions for us as long as we enter in the correct formula. And we can see kind of it down here. We can do combinations, and then it is basically just combinations referencing specific cells for our X values or the possible outcomes. and then basically plugging it into this formula. So there are ways that we can kind of streamline this using Google Sheets if we really wanted to. Or again, we have kind of the old standard pen and paper version that we kind of did together. But again, the main thing from this lesson, I'll scroll back up to it, is looking at binomial distributions, which has a specific number of independent trials. Each trial has only two possible outcomes, a success or a failure. So we have a specific formula to calculate the probability, and then a specific formula for the expected value, rather than going through and doing the sum of x times px. So this is our second specific type of distribution, adding on to the uniform distributions that we looked at previously. And we will have one other type of distribution that we will look at in the future.